Okay, so question 5 is we've got this graph here of the binding energy per nucleon, and very important, we need to see that it's in mega electron volts, and we're looking down the mass number here. So it's the graph where as we move up it, we're moving to a more and more stable kind of atom. So let's move on to the first part of the question, which is to do with state the number of nucleons in the nucleus of Rubidium 94. Rubidium, so the nucleons, you should realise the nucleon number is the top one, so for that, that's 94. The proton numbers, the number of protons now we've got in this cesium atom, the proton number is this number at the bottom. So in this particular cesium atom, let's write that out better, there are 55 protons. And the third part, state the number of neutrons in the nucleus of uranium-235. Well, what we need to do now is combine these two numbers together in such a way that we get the neutrons, and the nucleon number is the total number of protons and neutrons, and we've got 92 protons. So if we go 235, take away 92, and that will come out as being, I haven't got a calculator, quickly putting myself on the spot, so we're going to have 3, 4, 1, so 143 neutrons in that one. So moving on to part B, we need to use the figure above to calculate the energy released when a 235 uranium nucleus undergoes fission, producing nuclei of rubidium 9437 and cesium 14255. Okay, so we need to come to the graph, and we've got to find out, I've got the graph here, might be a bit small, but hopefully you've got it in front of you. I disagree with the mark scheme actually on this, and I'll show you why. So let's just get a pen, let's go for a red to make it a bit thinner for us. So if we're looking up for uranium-235, your graph is probably better than the one I can see here, but if we follow up for 235, assuming that's 200, that's 250, so it's going to be 6 little squares back, 1, 2, 3, 4, 5, 6, so that's this one. It's a bit hard to draw on this screen, and we're coming to that point there, and if we follow that line across, which is this one, I think is there, I think that is reading at around about 7.4 or 7.3, so maybe I do agree with the mark scheme. I think on your ones it might look a little bit different, but we can talk about that in class. So we'll say it's 7.4, and of course our unit is mega electron volts. So let's go back to the question. Let's get a bit of a thicker pen. Let's go for a blue. Okay, so yes, the uranium is 7.4 MeV. So you can give yourself a mark if you didn't get the right answer for that. We also need to read off the graphs and say the same thing, so you should be saying that the rubidium is 8.6 MeV. You would be allowed a little bit of leeway, and so that's the rubidium, and the cesium is 8.4 MeV. So now what we need to do is we've got to work out our total binding energies of these nuclei. So remember that these nuclei energy is the binding energy per nucleon. So if we go back, we can see to this question, it tells us our nucleon numbers, so 94 for the rubidium, 142 and 253 for the uranium. So if we have a look, then our total binding energy, so what I need to do is I need to go for the uranium. Oh, still on the highlighter. So the uranium is going to be 7.4 multiplied by the 235. If I stick that into my calculator, that comes out as being 1739 mega electron volts. And I'm creating these other two atoms, the rubidium and the cesium, and the rubidium is 94, so let's go 8.6 multiplied by the 94, and that comes out as 808. And finally the cesium is 8.4 multiplied by 142. What's just happened there? Not entirely sure what just happened there. My tablet just turned off, but we'll carry on. Hopefully it's all good. 8.4 times 142, and that comes out as being 1193 mega electron volts. Let's put that in up there as well. So the total energy released is going to be the binding energy of the products, so that's 808 plus 1193, take away the original binding energy, which is 1739, and if we stick those into our calculator, that comes out as being 262 MeV. Okay.